This is the test review for Chapter 5 and 6. Let's look at number 1. Oil is being pumped continuously from a certain oil well at a rate proportional to the amount of oil left in the well. Okay, that is dy over dt is equal to ky, where y is the amount of oil left in the well at any given time. Initially, there were 1 million gallons of oil in the well, and 6 years later, there were 500,000 gallons remaining. So we can create ordered pairs here. We know that everything is in the form of time, representing will be the x value, and then oil is the y value. Okay, so we know that at initially time 0, there's going to be 1 million gallons of oil. 6 years later, 500,000. So we'll be able to use these ordered pairs as we figure some of the missing variables. So part A, write an equation for y, the amount of oil remaining in the well at any time t. So we have the differential equation, dy over dt is equal to ky. So we take the steps to separate the variables. Y is on the left, everything else on the right. Apply the appropriate integral rules. So dy over y becomes natural log of the absolute value of y. K becomes kt plus c. We raise both sides with base e so that we can get rid of this natural log, so that we can get this y by itself. So this becomes y. And the right side, e to the kt plus c, we can split this up into e to the kt times e to the c. Now e to the c is just a constant, so we can pull that in front as c. So we have our general equation, y is equal to ce to the kt. We want to write the equation for y, so we need to find the c value and we need to find the k value. Okay? And that's what these ordered pairs are going to help us with. To find the c value, I can simply plug in 1 million in for y and plug in 0 for t. And if we go through that step, we're going to see that e to the k times 0 is simply 1. So c is equal to 1 million. So y is equal to 1 million e to the kt. So that gets us closer to the particular solution. Now we need to find the k value. So we look at the other ordered pair, 6, 500,000. So 500,000, let's plug that in for y. 6 is 6 years, so let's plug that in for t. So once we have that, we get 500,000 is equal to 1 million e to the 6k. We want to solve for k, but first we want to get e to the 6k by itself. So let's divide both sides by 1 million. So 500,000 divided by 1 million is simply 1/2. So we get 1/2 is equal to e to the 6k. We want to bring down this k. So to do that, this is sitting up as an exponent. We can introduce logs to both sides of the equation, and that way we can use the power property to bring that 6k down. So I'm going to rewrite 1/2 as 0.5. So take the log of both sides. Natural log of 0.5 is equal to natural log of e to the 6k. Bring down that 6k, the natural log of e drops out. So we can simply now solve for k. K is divide both sides by 6. So k is equal to 1/6 natural log of 0.5. So now we have our specific equation, now that we have the c value and the k value. So y is equal to 1 million e to the 1/6 ln 0.5 t. Okay, so that's part A for number 1. Part B, at what rate is the amount of oil in the well decreasing when there are 600,000 gallons of oil remaining? So 600,000 gallons of oil remaining, that's represented by y equals 2. Okay, so y represents the amount of oil. So 600,000 is the oil that is provided in this problem. But part B says, at what rate is the amount of oil decreasing? So we're trying to find dy over dt. So let's look at what equation that we have with dy over dt, and that is the differential equation, right? So dy over dt is equal to ky. We're trying to find what rate is the amount of oil decreasing when y is equal to 600,000. Well, we can plug in 600,000 in for y, And then with the k value, we found that from part A. So we know that our k value is 1/6 natural log of 0.6. So we plug that in for k. And we just plug that in our calculator to get our dy over dt. So the amount of oil is decreasing at a rate of 69,314.718 gallons per year. This is rate, so we have to write it as our units in terms of a rate as well. Okay, part B. Right, it is no longer profitable to pump oil when there are fewer than 500,000 gallons remaining. In order not to lose money, at what time t should oil no longer be pumped from the well? So basically, we can take our specific equation and figure out how much time will pass when 500,000 gallon remains. So we take our specific equation, replace 500,000 in for y, and then we take the steps necessary to solve for t. So we get 500,000 is equal to 1 million e to the 1/6 ln of 0.6 t. We want to eventually solve for t, but we need to get this e to the 1/6 t by itself. So let's divide both sides by 1 million. So 50,000 divided by 1 million is simply 0.05. Is equal to e to the 1/6 natural log of 0.5 t. We want to bring this exponent down, so we introduce natural log to both sides. Once we do that, this 1/6 natural log of 0.5 t can come down in front. The natural log of e just drops out. So we're just left with this expression, this equation. So to solve for t, we just divide both sides by 1/6 natural log of 0.5, or that would look like 6 natural log of 0.05 divided by natural log of 0.5. Solve for t, so t is equal to 25.932 years later. Okay. So number 2 says consider the differential equation dy over dx is equal to x squared times y minus 1. On the axis below, sketch the slope field for the given differential equations at the 15 points indicated. So all we do is identify all the ordered pairs that's highlighted and plug each of the ordered pairs into the differential equation, and whatever value is returned, then you just sketch that slope. So for instance, all these are where x is equal to 0. So if I plug 0,3 or 0,2 or 0,1, it'll produce 0, so that's where my slope will be. Slope segments will be 0. So we do that for each of the order pairs, and we fill out this slope field. Okay, part B says, while the slope field in part A is drawn at only 15 points, it is defined at every point in the xy plane. Describe all the points in the xy plane for which the slopes are negative. So now, since x squared is always positive, the negative is not going to come from the x squared. The negative is going to come from the y value. So the only time that this expression will become negative is when our y value is less than 1. Okay? Once it gets less than 1, then that expression will become negative, and that's going to force this derivative to be negative. So we can say that since x squared is always positive, the determining factor is the y value. When y is less than 1, then our derivative is less than 0. Okay, so basically, all the points below the line y equals 1 will have a negative slope. Okay, part C, find the particular solution y equals f of x to the given differential equation with the initial condition 0,3. So let's look at our differential equation, which is dy over dx is equal to x squared times y minus 1. We take the first step to separate the variables. So we get dy over y minus 1 is equal to x squared dx. Okay, we take the integral of both sides. The left side is simply the rule for natural log of, or 1 over u, which is natural log of u, so natural log of y minus 1. The right side is power rule, so x cubed over 3 plus c. raise both sides with base e, so we can get this y minus 1 out from this natural log function. So we get y minus 1 is equal to, and the right side, we can split this up into two terms, e to the x cubed over 3 times e to the c. Again, we know e to the c is simply a constant, so we can represent that as c, pull that in front. So we get y minus 1 is equal to ce to the x cubed over 3. Okay. Next step, we want to plug in our initial condition. So 0, 3. 0 plugs in for t, and 3 plugs in for y. So we get 3 minus 1 is equal to c e to the 0 over 3. E to the 0 over 3 is simply 1, so c is equal to 3 minus 1, which is 2. So we have our initial condition used to solve for c. Once we have the c plugged in, we can write our specific equation. So therefore, y is equal to 2e to the x cubed over 3 plus 1. All right, part D, find the equation of the line tangent to our function at point x equals 0 and use it to approximate f of 0.1. Now, the ordered pair that we have is 0, 3, so that's already given to us. The only other thing that we need when we find the equation of a tangent line is we need to find the slope. Okay? So to find the slope, we can simply plug in to our differential equation. So plug 0 in for x, 1 in for y, and then we get our derivative being simply just canceling out to be 0. So our slope is 0, our ordered pair is 0, 3. Plug into our equation, point slope form. So y minus 3 is equal to 0 times x minus 0. All this is simply just going to cancel out to 3. So y of 0.1 will remain at 3 because that's just going to be a straight line. So there's nothing to plug in here because our tangent line equation is just going to cancel it to everything out to just simply be 3.